In this video, we want to look at Bohr's theory and electronic configuration of elements. Now, first of all, you may have to get your writing materials to write down some things. For Bohr's theory, the first one, he says that electrons move round the nucleus in a circular pattern. So if we have that this is the nucleus of an atom, he says electrons move round a definite pattern. So they move in a circular pattern. This circular pattern is called orbits. The number two theorem is that as long as electron remains in an orbit, radiation does not occur. The third one is that radiation only occurs when electrons move from one higher energy level to lower energy level. So when they move from higher energy level to lower energy level, then radiation will occur. So let's now go into electronic configuration proper. Electronic configuration actually is the arrangement of electrons in orbitals or energy level. So we have principles that govern the distribution of electrons. The first one, we call it the Aufbau principle. Let me write it. Aufbau's principle. So sometimes books will call it Aufbau's building principle. So Aufbau states that electrons are filled in orbitals in order of increasing energy level. So what it means is that you begin with smaller energy level and you keep increasing. So that's what the first one. The second one is Horn's rule. Horn's rule. So we call it Horn's rule of maximum multiplicity. So Horn's rule of maximum multiplicity states that electrons are filled in orbitals or orbital degenerating singly before pairing. So when we're filling, we fill them singly first of all before we pair them. The third one is the one we call Pauli's exclusion principle. Pauli's exclusion principle. And he says that not more than 2 electrons can occupy an orbital and they must be in opposite spin. So what it means is that if an electron stays this way, another one wants to also be in the same orbital, it will have to be the opposite direction. So that's what Pauli's exclusion principle. And we have a way of filling, which is from lower energy to higher energy level. We have the S1, we have the 1x, 2x, 3s, 4s, 5x, 6x, and so on, 7s. And then after the first one, we have the second one, which is the P. So here is 2, so 2p. So after 2p, we have here is 3, we have 3p, 4p, 5p, 6p, 7p. So this is how to fill. You first of all put 1x, then you put 2x, then you fill in 2p, 3x in this direction, in this direction. This is how you fill. Then this is how we fill it. So while filling, we need to note that the s orbital takes maximum of 2 electrons. The p orbitals take maximum of 6 electrons. The d orbital takes maximum of 10 electrons. And the f orbital takes maximum of 14 electrons. So while doing this, let's say for example, we have the shells let's first of all look at the shells, and in a circular form, and it keeps on going. The first one is called the K shell. K L K L M N O to R. It keeps increasing to R. All right, let's say for example, we want to put an electronic configuration for, let's use hydrogen for example. Hydrogen, just one electron, and it means that K is the one that has that electron. K has maximum of 2, L has maximum of 8, M maximum of 8, and so on. We'll be seeing that. So K only takes that. So we have just 1s1. So that one electron, the S takes it because it's the first, the lowest energy level. And if we have helium, helium is 2 electrons. So 2 electrons, it means that K having maximum of 2 will take those 2 electrons. So we also have 1s will also take that too. And also if we have something like boron, we want to represent boron. Now boron has 5 electrons, and if we want to represent that, K takes 2, then remaining 3. L having maximum of 8 will now take the remaining 3. So if we want to write it out, we can say 1s2. After 1s2 we have 2s2. 4 is already gone, is now remaining 1. That one now goes to the, that's this takes 2, this takes 2. The next one is now 2p. So 2p will now take the remaining 1 that is there. If you want to represent it, because remember helium takes is 1s2, you can represent it by saying helium, which is 1s2, and then 2s2, then 2p1. This is another way you can write it. If we have another example, let's say carbon. Now carbon has 6 electrons. So it has 6 electrons, 6 protons, and then 6 neutrons. It means that what you have is K will take 2. If K takes 2, is remaining 4. L, remember, is supposed to contain 8, so he will now take the remaining 4 that is left. If we want to write it out electronically, you write 1x2 takes this one, 2x2 takes 4 is already gone, remaining 2. So P now takes that remaining 2. Remember, it's supposed to contain maximum of 6, so remaining 2, you will now take that 2. Another example, if you have something like let's say argon. Now argon has 18 electrons. So if we want to write it out, K shell takes 2, L shell takes 8. Remember, 10 is already gone. Then M shell takes 8. So if we want to write it out electronically, 1x2 take 1, it takes his own, 2s2 takes 2p6. Now remember, 10 is gone, remaining 8. Then we go back to 3s2 and then 3p6. So it's complete. Another example is if we look at neon. Neon has 10 electrons. So if we want to represent neon now, we can say 1s2. After 1s2, we go to 2s2. After that, we have 2p6. So this is 10 complete now. That is why most times or sometimes argon can be written as, because if you look at here, you can see this is neon. This is neon. So you can write argon as neon, then you now write 3s2 3p6. This is another way you can write argon. Let's look at another example. Let's look at, for example, copper. Copper has 29 electrons. 29 electrons, that's it also means that it has 29 protons but 35 neutrons. So if we fix it, this one, K takes 2, L takes 8, M takes 18, and then N takes 1. So that's how they are arranged in their shells. But if you want to write it electronically, we'll first of all begin with 1s2, 2s2, 2p6, 3s2. Then after that we go to 3p, 3p6. Now we'll check, here is 10, 12, and then 18. 18 is already gone, and someone that has 18 is also argon. Argon also has 18, so it means this person is argon. After argon, you can write 4s1 and then 3d10. That's why sometimes copper can be written as argon, and then, sorry, after argon, you now have 4s1 and 3d10. So sometimes you can write copper this way. Also, another one, now there's something we need to note. We need to note that there is nothing like D4 or D9. It does not exist. That is why chromium is written as, if we're to write chromium, for example, chromium has 24 electrons. 24 electrons, that means 24 protons as well, and then 28 neutrons. Now, if you are to write it out in terms of shell, K takes 2, L takes 8, and M takes 13, then N takes 1. Now, what anybody would have loved to write is, since argon has 18 electrons, so 18 is already gone, which means 6 is left. So the person would have just, let's say, you now write maybe 3d4, and you now want to fill your s2. You now say 4s, you fill it like this. This is wrong, because there is nothing like d4. Is wrong. So for you to write chromium, chromium takes this form: Ar, wagon 18, already gone. So 3d 5, and then 4s, you give him 1. Now the reason is because chromium is a transition element, and transition elements like chromium, copper, cobalt, like copper, if you see copper, cobalt, nickel, vanadium, iron, titanium, gold, mercury, all of them, they have either partially filled d orbital or completely filled, which is they have either d5 or d10. If you look at copper, you see d10 or d5. That is how they exist. So their d orbitals are either partially filled or completely filled. Now when we talk about okay, let's also look at aluminium. Aluminium has 13 electrons, 13 protons, and 14 neutrons. So if we want to write it, K takes 2, L takes 8, and M takes the remaining 3. This is 10 and 3, 13. Then if we want to write it electronically, we have 1s2, we have 2s2, and also 2p6. 10 is already gone, remaining 3. So 3s takes 2, remaining 1. So that one goes to 3p1. So this is how to write, or you can write it as neon. Neon takes 10. So you now have 3s1 and then 3p1. So feel free to subscribe to my video. Thank you.